if you remember what we were discussing last time, so we had holomorphic Chern-Simons theory on SL2C. The neighborhood of the boundary looks like has coordinates n, z, w, where w is on a CP1. N equals 0 is the boundary. And there was a Beltrami differential which changes what functions are holomorphic. Which looks like n squared dw bar lz, and also n transforms as like dw to the half. So what we wanted to do was study fields of holomorphic Chern-Simons theory which satisfy the equations of motion and violate the boundary condition at a point in the z plane. So the boundary condition we asked that our gauge field is divisible by n, so that on the boundary it vanishes. In algebraic geometry terms, it's a section of the line bundle O minus d, where d is the boundary. Okay? So a solution to the equations of motion which violates the boundary condition is given by A, which looks like a delta function at z equals 0 times some Lie algebra element plus there's a correction term, n squared times n, factor of n, 1 plus v squared dw bar times 1 over z squared. So last time we saw, like, you could introduce higher order poles in n here, and that forces you to have more and more terms, but there was like completely explicit solutions to the equations of motion, the linearized equations of motion, which just violate the boundary condition along z equals 0. So if I take a z0, a, and a z1 a1, I can take 3 such guys which violate the boundary condition at these points, and then we can try to define the holographic 2- and 3-point functions according to Witten's prescription. This is going to be the integral over the full 6-dimensional geometry of 0, A0, B bar, AZ1, A1 times the holomorphic volume form. And similarly, the 3-point function is the integral az1, 1, az2, a2, times the holomorphic volume form, but of course I forgot to put here, I take, we put the killing with the invariant pairing of the Lie algebra, and here we put the trace of the product of the Lie algebra elements. Okay. So any questions about how setup works? Like what we're trying to do? Right, so this, yeah?
Tree level.
Yes, yeah. And so it's the tree level from the point of view of this, of the holographic dual setting, but from the point of view of the chiral algebra, this will compute the planar 2- and 3-point functions. And the way, I mean, well, if you read Witten's paper, you would draw something like this. Here's ADS3. I have 3 points in the boundary, which are these z's. I modify the boundary condition, that sources some field, and I plug those 3 fields into the cubic term of the action, and I integrate it. And similarly here. So for the 2-point function, I think what Witten would say would be you look at the field source by 1 point and how the subleading terms behave at the other point. But if you think about, it's a bit off topic, but if you think about the equation satisfied by the bulk to boundary propagator, this is the same as plugging in the kinetic term of the action. So let's first compute the 2-point function. And there's going to be a slight subtlety. So we want to view A as a section of a non-trivial line bundle, the line bundle of things which vanish on the boundary. So A is really a section in omega 0, 1 of the compactified SL2C with coefficients in O minus D, where D is the boundary divisor equals 0. Now, of course, away from the boundary, this line bundle is trivial, and we can view a section of O minus D as a section of O with a 0, or a section of O minus D with a pole is just a regular section of O. However, the D bar operator on O minus T is not the same as the D bar operator on O. So, if near the boundary, we write A as a function, a section of O, then like the D bar operator on O minus D looks like D bar is the usual D bar operator conjugated by N. So the reason is, as the function 1 viewed as a section of O minus D has a first order pole. So if I take D bar of it, viewed as a section over here, I must pick up a delta function. And that is achieved by this conjugation. Okay. So let's... so I hope you can believe that, and now we can compute the 2-point function. So the integral of a z0, so we have this formula. So if this was a z0 here, then in the first term I had a delta function z equals z0. So this will give me something like the integral of, well, it turns out that this first term not really going to matter the way we've presented it, because d bar of this is 0 except at z1. So hitting d bar of this with the delta function at z0 is going to vanish. So only the second term in there can contribute. So this will be n squared dw bar over 1 plus w bar squared. Then 1 over z minus z0 squared. And then d bar of this I think that's right. Yeah. So then times the volume form, which looks like dn dz dw over n cubed. And this term is crucial. The fact that I have to change the meaning of d bar, like the fact that this guy violates the boundary condition, I mean, it means that d bar of it acquires a pole. Because viewed as a section of O minus d, it has a pole. So here I pick up integral n dw bar over 1 plus w squared 1 over, this is z1, z1 minus z0 squared, and then dn dz, well, get rid of the dz, because I've done a delta function. And let's calculate the powers of n. What am I saying? No. I've got rid of the dn too because of the delta function. Sorry, the equation I'm using is d bar of n minus 1 dn is a delta function. So this dn is being used up. So now because I have the delta function in the n direction, I don't integrate over n, I don't integrate over z, I only integrate over w, as in this is proportional to 1 minus z0 squared. Okay. Does this calculation make sense to you guys? Oh, yeah, or, yeah? Okay, so this is good because this boundary state corresponds holographically to the current for a GLK/K action. So in the chiral algebra, so if I have these fields I, and J, in Cn, Ck/K, the OPE of I and J includes 1 over z squared times n.
Why do we need to work in square root, not with GLK?
Because of the there's an anomaly to defining the BRST reduction. So if I just said CK, that anomaly would appear, but it cancels in the sigma group case. There are variants of this story where in the bulk you could use SO, but you can't use GLK. So the 2-point function of this guy is like n for z squared. Okay, it's correct. Okay, so let's quickly do the 3-point function. Is there any other questions? Any other questions? So it's actually, to actually compute this 3-point function, one has to perform an integral over all of SL2C of some explicit quantity. And being rather lazy, I don't want to do that. So what I'm going to do instead is write the 3-point function in terms of the OPE, the 2-point functions. So better, one an OPE. So given 3 fields, say 2 fields, AZ0, AZ1, which violate the boundary condition at z equals zi. So we want an OPE AZ0 times AZ1 you want to do an expansion, just like in a vertex algebra. You want to expand it as a sum, which is singular powers of the difference between the two of them, times some other quantities, where a tilde I C0 are some fields which violate the boundary condition at C0. So how do we, of course the OPE constraints are going to contain the same data as the 3-point function. So given these fields of the holographic dual theory, it must be the case that if I stick the right-hand side into the 2-point function, that's going to be the same as sticking the left-hand side into the 3-point function. So we must have, so if A tilde tilde, say Z2, is another field. We must have the integral of AZ0 wedge AZ1 wedge AZ2 tilde tilde is equal to the sum I greater than 0, 1 over Z0, C1, the I, the integral So if I take these guys and I evaluate their 2-point function with respect to some test field, that must be the same as taking the 3-point function over here. So that's the definition of the OBE. And plus regular terms in Z0 minus C1. So actually, it's going to be convenient to put this on the other side. This E bar over there. So clearly, the solution to this, a solution to this can be obtained if this quantity is D bar inverse of this guy. So is equal to plus regular terms. So what we need to do is take the wedge of these guys, apply D bar inverse, and then just take the expansion in terms of Z0 and Z1. So fortunately, we can do this. We can do this completely explicitly and calculate the OP. So we'll like AZ0 as before. I'm going to drop the Lie algebra indices. Plus n squared W bar squared LZ. Z squared. We take AZ1 to be the same kind of thing, except at Z1. Well, you notice that AZ0 is nothing but the bar of 1 over Z minus C0. So I can remove this field by a gauge transformation, which sends it off to infinity. So the reason it looks like this is that, if you recall, the D bar operator was not the naive one. It had an extra term involving this expression times d by dz. So therefore, one over z minus c0 az1 is e bar inverse and if you look at this, this is 1 over z1 minus z0 times the delta function, z equals z1. So this is like very much the kind of OBE thing. And there's going to be some other term, but you can fiddle around with it, with the other term, and you realize that the other term looks like that. So, right, so if I wedge them together and apply d bar inverse, then what's regular terms? You can expand it in powers of z1 minus z0, and the only term you find is 1 over z1 minus z0 times the same expression. Okay, is this making sense? So the answer is the holographic OBE has 1 over z1 minus z0 times the same kind of thing. So if I take AZ, we introduce into the algebra indices, this AZ1A1 looks like F A0 A1 A2 1 over Z0 minus Z1 AZ0 A2. Okay. So we've already computed the other term, the 2-point function term. So I hope this expression is familiar to everybody. This is an expression for the Cas-Moody algebra. So these calculations show that like the very first operators we see satisfy the OBEs of the Cas-Moody algebra at level n. So this is level n Cas-Moody for DL A/K. And of course, this also appears in the large N Carroll algebra just because we have something with the GLK/K symmetry, so there are occurrence for that, and they have the same level. Yeah. Any questions? So you guys all think you can compute holographic OPs and okay, so what do you think I should do? I mean, let's see. So we have some feeling for the large N Carroll algebra. We've written down some operators in it. We've done some holographic computations, and they match. And you can go further and show that everything matches with a lot of work. What would be useful for you guys? I mean, I could, there are two directions I could go on to, say why they match, and talk about the global symmetry algebra, which is some kind of trick for comparing things, or look at other examples.
Is it hard to compute the closed field, like trace X and trace C?
Yeah, that's a great question. So, the Kadir-Spencer propagator is really nasty. So you can do it, but I'm not going to be able to remember at the board how to do it for that piece of the closed string structure. But for the fermionic closed string fields, you can do it. And it's let me say, And it's actually just the same. So let me briefly explain that. So here in the chiral algebra, you have things like trace of B times Z I1 Z IK, and trace of del C times Z I1 Z IK. Are these the usual BC ghosts implementing the BRST reduction? And these are fermionic. And they're given the spin k over 2 rep of SE2 core, and our dimension k over 2 plus 1. So on the holographic, so Kadeira-Spencer theory includes something you might call holomorphic Chern-Simons, for the abelian in the algebra which is an odd copy of C2. So because it's holomorphic Chern-Simons, you can do like the same thing we just did. So this involves a slightly funny way of rewriting Kadeira-Spencer theory. So these come from PV0 star and PV2 star, the kernel of del inside there. But actually, the trick is to replace this by the image of del. And then you get two fields, both of which live in the double complex. Yeah, for these fields, like the calculation is just the same.
Is there any non-trivial PVs movement close to?
Yeah. How does it work? Goes both ways, actually. There's, is that right? No, actually, the one from open to open to close, taking open to closed, is that subleading order in the Warner-Bryan expansion. But there's a closed times open to open OPE, which takes, for example, like trace of Z1 and trace of I Z2J. These have an OPE, or I contract the things in the middle, 1 over Z twice. So there are things like that. And again, like in principle, you could be able to compute those holographically. I think we have more detail on this point on our paper, but at the blackboard, I'm not going to be able to write down the explicit formula that we did for the Chern-Simons case. Okay, so what? So should I continue trying to explain why this is true or move on to other examples? Any thoughts? At this point? Okay, this is actually a very good thing to know. So I think, this is fun, so I'll say a little bit about this. So the way Kodaira-Spencer theory was originally set up you have some Beltrami differential X is a Calabi threefold. You have some Poisson tensor. And you have some scalar, I'll call gamma. It's called Zaltzer. And the action looks like, I would say just writing down the kinetic terms, d bar alpha del inverse alpha plus integral gamma, d bar gamma del inverse pi plus interacting terms. Now, and obviously this only makes sense if pi and alpha must both be in the kernel of del. Like if you write things in the de Rham complex, this must be a 1 star form in the kernel of del, and this is a 2 star form in the kernel of del. Now, clearly there's something a little silly going on. Okay, I mean, it's kind of hard to get rid of this del inverse, but this del inverse is unpleasant and easy to get rid of. So it seems silly to include it. So you simply write pi as del beta, where beta is in PV 3 star, which is equal to omega 0 star. And that's it. And then we have, and the kinetic term looks like and you can write out the remaining terms too. So this. So what we see is the piece with just the Beltrami differential coupled to a beta gamma system in the most natural way, minimally coupled. So this is actually a much better way of writing Kodaira-Spencer theory. Because one reason is it exhibits a symmetry that you had not seen before. This guy has an SL2C action, which rotates beta and gamma. And well, looking at that, you might think it might have something to do with S-duality. And that, if you think a little more about it, you'll realize that this guy here, which is really like a function, well, in the original paper of Vafa and collaborators, the Gauss number 0 field here was a 0,2 form, which they thought of as a gerb. But really, gerbs are not 0,2 forms. They're 0,2 forms up to integral stuff. So this guy should really be a function up to integral stuff. So really, gamma should be valued in C star. And you can also guess that beta is valued in C star. Better. Beta and gamma define a map from X to C star squared, and we're coupling alpha to holomorphic Bolzanski-Witten theory. On C star times C star. Now, because this is a two torus, SL2C group has been broken to SL2Z. Which is natural to conjecture is given by S duality. Now, in the chiral algebra, you expect it's associated to n equals 4 Yang-Mills, which should have S duality symmetry. And you can, by this, you can really see S duality explicitly at infinite n, or even at finite n. It's extremely subtle.
Can we also see the change of case group?
Oh, that's a great question. That's a subtle issue in all string theories, right? Because to see SO versus SP, you need to use orientifold planes. I don't really know how to use orientifold planes in the topological string, but that would be great. But I don't know how to do that. I can't even really. I can't even really see the difference between SL and PSL. Any other questions? Yeah. So maybe I'm still not sure what exactly this course is going to be about, but maybe next week should we move to different examples? Holography. We could talk a little bit about causal duality as well. Yeah.